So welcome to the students. This is the week 4. So welcome to this session. I welcome you all. Actually, in this session, we will discuss or we will learn a new process or approach that is known as integration, right? So naturally, if this is a new approach, so it also needs some methods, some techniques. So after having the idea of integration, we will further discuss the various tools and methods which will help us to find out the integrals of the various kinds of functions. So integration overall and their methods, and then for subsequently we will discuss some applications of the integration in business and commerce, etc. So let us start integration. We know that for a given function f, we can always find out its derivative, right? So if we can find out the derivative of a function f that is denoted by f dash x, so a natural question arises, if instead f dash, that is derivative of f, is given, can we find out the original function? It's a natural question. So it's a natural question because if you take the real example of our day-to-day life, what happens with us if we expose a piece of ice into the air, and the piece of ice is considered as a solid, it gets converted to the water. So what happens? The temperature of the atmosphere in which the piece of the ice is being exposed acts as an agent or catalyst to convert a solid piece of ice into its liquid position. So we are converting a solid into liquid, and naturally, is it feasible to reverse the process? The answer is yes. If we put that water inside a refrigerator, then it again gets converted to the piece of ice. So the temperature of the refrigerator now acts as an agent or catalyst which converts the liquid into the solid state as an ice. So by this example, we will use the same approach here. That is, if f is a function and we are finding out its derivative f dash by the process of differentiation, so the natural question arises whether the derivative of a function f dash is given, is it feasible or it is possible to restore our original function or not? So the answer of this question is yes, and this question can be solved with the help of a process which is known as integration. So naturally, integration is in general inverse process of differentiation, right? Whatever function we have differentiated, we can reverse that derivative to restore our original function through the process of integration. The set of all functions which are obtained from its derivative are called antiderivative of the function. Antiderivative, it is called as antiderivative because integration is just the inverse process of differentiation. So we can use the word antiderivative or integral, both are same. Further, the process which gives all these integrals or all these antiderivatives are called integral, and the process itself is known as integration. There are many such practical and theoretical situations where the process of integration is involved, and as a whole there are two branches of mathematics. One is the differential calculus and the other is the integral calculus. So differential calculus in fact talk about derivatives of the functions. Likewise, integral calculus talks about the integrals of the various kinds of function. So what we observe from this single slide, that is, integration is generally the reverse or the inverse process of differentiation. And what we did in differentiation, differentiation simply talks about if you have given a big object, it can be decomposed into its smaller parts, right? This is the process of differentiation. If you have any big object, you can decompose it into their smaller parts through the process of differentiation. On the other hand, if you want to reverse it, accumulate all these smaller parts to get its original part. So differentiation talk about disintegration. On the other hand, integration talks about the total accumulation of an object or a quantity itself. So it's all about the basic idea of integration. I hope you understand. The basic or the single line definition of the integration is what? The inverse process of differentiation is simply known as integration. Let us have its mathematical approach. See, we know that dy over dx, that is the derivative of the function x4 upon 4 is what? That is x cube. Clear? Because derivative of x4, we know that 4x cube, 4 and 4 will be cancelled out, you will get as x cube. See this, x4 divided by 4, its derivative is what? 4x cube divided by 4. So what we will get here? We will get here x cube, right? So derivative of x4 upon 4 is x cube. So what we observe from this equation, see, we can observe from the above example that x cube is derived from the function x4 upon 4. X cube is derived from the function x4 upon 4 means x cube is the derivative of the function x4 upon 4. And I have just told you integration is just the reverse process. So if x cube is the derivative of x4 upon 4, then naturally x4 upon 4 is considered as antiderivative or integral of the function x cube. Are you getting the point? Let us see it diagrammatically. What we did here, x4 upon 4, this is x4 upon 4. Its derivative, d for derivative is what? X cube, right? So through the process of differentiation, the function x4 upon 4 has been converted to x cube. Now our objective is what? What would happen if what kind of act should be done with x cube? So if we integrate x cube, we will get our original function x cube x4 upon 4. So if x cube is the derivative of x4 upon 4, then by the definition of the integral, x4 upon 4 is known as antiderivative or integral of the function x cube. And not only x4 by 4. So see, if derivative of x4 by 4 is x cube, if we add a constant, for example, x4 by 4 plus any constant, any number, then its derivative is still x cube. See, derivative of x4 upon 4 plus c is still x cube. Thus, antiderivatives or integral of the above cited function are not unique. What is the meaning of unique? Unique means not only one, more than one. Right? So how we can get more than one? See, derivative of x cube is also x4 upon 4 and derivative of x4 upon 4 is also x cube and derivative of x4 upon 4 plus c is also x cube. So x4 upon 4 plus c is what? If c is 0, you will get x4 upon 4. If c is 1, you will get x4 upon 4 plus 1. If c is minus 5, you will get x4 upon 4 minus 5. So derivatives of all such function is a single, that is x cube, right? X cube is not the derivative of only x4 upon 4, but all those functions of the type of x4 upon 4 plus c, c being any number or any constant. So there are infinite many functions of the type of x4 upon c whose derivative is a single function, that is x cube. So naturally, if we will integrate x cube, So we will get x4 plus upon 4 plus c. There are infinite many integrals of a single function x cube, which are known as x4 upon 4 plus c. I think the concept should be clear, is it? But what I want to explain here, x4 upon 4 is not the single function whose derivative is x cube. If we add any constant or we subtract any constant in x4 upon c, its derivative is again x cube. So what it means, there are many functions, almost infinite many functions. We can get infinite many functions by changing the value of c. So there are infinite many functions of the type x4 upon 4 plus c whose having single function x cube as its derivative. So naturally we are just reversing the process. So x4 upon 4 plus c is an antiderivative or integral of the single function x cube. It means x cube is not having only one antiderivative, rather it is having infinite many antiderivatives as x4 upon 4 plus c. We can get infinite because by changing the value of c, the function x4 upon 4 will also change, right? In general, what we conclude, if capital F is any function such that derivative of the capital Fx is fx, right? For any function, for any real number c, any constant, derivative of f of x plus c is fx, right? So this fx plus c is a constant, and as I have told you, change the value of c. By changing the values of c, we will get a number of functions. So f of x plus c denotes the family of antiderivatives of fx, or f of x plus c denotes the family of integrals of fx, where c denotes the constant of integration, right? Clear? After having the idea of this integration, now we will use some notations as we did in case of derivatives. We are having a number of notations for the derivatives. So likewise, we will also use some specific notations for integral, right? So this is the sign of the integral, right? And what is this? Fx dx. This is how we read, right? And this is how we write. And how we read it? We read it integral of the function fx. This simply refers to integral of the function fx. This sign is what? This is the sign of the integral. Fx is the function whose integral we want to calculate or we want to determine. It is also known as integrand. And dx is any dummy variable with respect to whom the function fx will be integrated, right? But be careful, the variable x and dx, they should always be same. They cannot be changed. For example, if I write here f of t, then here we will get here dt, right? See, this t and dt both should be same. If I write here f of p, then we will write here d of p. So these two must be same, right? So fx is known as the integrand. Integrand means the function whose integral we want to calculate, and this is simply the sign of the integral. X is a dummy variable with respect to whom the function fx is going to be integrated, right? Symbolically, we write it like this. The integral of fx dx means what? If the integral of small fx is coming out to be, say, capital Fx, then it should be written as fx plus c, where c is known as the constant of integration. You should be very careful in adding this constant c. If the constant c is not added, your integral may not be considered as a correct. There is a reason. If you write here only f of x, for example, so f of x is only one function. But f of x plus c, it means what? If c is 0, you will get f of x. If c is 1, you will get f of x plus 1. If c is minus 5, you will get f of x minus 5. So by changing the values of c, we can have a number of functions, almost infinite number of functions, right? So C is very important, you should keep in mind, and this C is known as the constant of integration. Okay. Now let us see some standard formulas. So please recall the concept of derivatives. What we did in derivatives, we have seen there were certain functions or standard functions whose derivatives are already known, like x raised to the power n, e raised to the power x, a raised to the power x, log x, etc. Likewise, there are certain functions whose integrals are already known, right? I have given this in the table because integration and differentiation both are inversible, both are inverses of each other. So see this table very carefully. Derivative of x you know is 1, right? Derivative of x is 1. So if derivative of x is 1, see this, what we want to show, derivative of x is 1. This is derivative. Then integral of 1 should be x, right? This is what we want to show. So integral of 1 dx is x and c is always there. Derivative of x raised to the power n, we know the formula was xn, its derivative is xn plus 1 divided by n plus 1, right, plus c. This is the integral of x raised to the power n, right? And what was its derivative? Derivative of xn was nxn minus 1. So see here, if integral of xn is this, then by the definition, if we differentiate this, we should get our original function, right? Check it. If we take y is equals to xn plus 1 upon n plus 1 plus a constant c, for example, find out its derivative, dy over dx is equals to c, 1 upon n plus 1 is a constant, it will remain as it is, right? And you know what is the derivative of xn? nxn minus 1. Here in place of n we are having n plus 1, so its derivative will be what? N plus 1 and x raised to the power n. C being a constant, its derivative is 0, so this and this will be cancels out. What is left? X raised to the power n, right? So integral of likewise 1 upon x is log x, because derivative of log x is 1 upon x. So in this way, these are the certain formulas which you should either remember or understand or keep in your mind, which we will use any one of these formulas subsequently in our questions whenever they are needed. Tell me one more thing, that is what? Take this formula. If y is equals to say ax plus b, what happens here? How this 1 upon a comes? Y is equals to say ax plus b, right? What is its derivative? Dy over dx is y is equals to 1 upon ax plus b. So what is the derivative of log ax plus b? Say, take this log, if y is log ax plus b, right? See, then its derivative is what? Dy over dx. You know derivative of log x is 1 upon x. So here in place of x we are having this. So what we will get? 1 upon ax plus b into derivative of ax plus b. B is a constant, its derivative is 0, and derivative of ax is a. So its derivative is what? A upon ax plus b, right? Be careful, this a is simply a constant, right? It's a number, and you know if 2 is a number, its inverse is what? Its inverse is, if 2 is a number, then its inverse is 1 upon 2, so that if these two numbers are multiplied, the product should be 1. So what I want to show here, all those numbers which lies in numerator, they will be automatically transformed in denominator, because integration is just the inverse process of differentiation. So keep this in mind. That is why integral of 1 upon ax plus b dx, this a comes in denominator, because of the reason if a is in numerator, A being a number, its inverse is 1 upon A. So it will transform from numerator to denominator, right? Let us take some properties. So properties of the different integrals are what? The process of differentiation and integration are inverses of each other. I have already discussed this thing. The process of differentiation and inverse and integration both are inverses of each other. Property 2 is what? If two functions are added up, see fx plus minus gx added or subtracted, then we can find out its integral by integrating them separately and adding them if they are added and subtracting them if they are subtracted, right? Property third is what? For any real number k, if a number k is multiplied with the function fx, then the function k can be taken outside from the integral and we will integrate the function fx. So these two properties are combined together. We have taken property number 2 for two functions fx and gx. If we are having more than two functions, for example, there are fn functions, f1, f2, f3 and fn functions, and k1, k2, k3 or kn are n constants, and if this kn is multiplied with the k1 is multiplied with the first function, k2 is multiplied with the second function, kn is multiplied with the nth function, and they all are summed up or subtracted, then this value is equals to, always a constant number is taken out of the integral. This k1 is taken outside. What we will do, we will integrate the function f1x dx. Likewise, k2 is outside, k3 is outside, and then so on. So keep this property in your mind. We will use this property almost in every question. What this property simply refers to, if two or more than two functions are added or subtracted, we can find out its integral by integrating first function plus second function. If two functions are there, if three functions are there, first function plus second function plus third function. If four functions are there, first plus second plus third plus four. So we can have addition of any number of functions as well as subtraction of any number of functions, right? Now come to the example 1. Evaluate the following integrals. The first case is x raised to the power 1 upon 3. So see, x raised to the power 1 upon 3. We know the formula of xn is what? The integral of xn is xn plus 1 upon n plus 1 plus c. Here what is the value of n? Here n is 1 upon 3. So its integral will be what? X power 1 upon 3 plus 1 divided by 1 upon 3 plus 1 plus a constant should be there. So what you will get here? X power 3 plus 1, that is 4 upon 3, and here in denominator 4 upon 3 plus c, and this can be written as 3 upon 4 into x power 4 upon 3 plus a constant c, right? This is your answer. So any power of n, as we did in case of derivatives, any power of n can be differentiated there. Likewise here, any power of n can be integrated by using the single formula of x raised to the power n, whether n is positive, negative, fraction or any number, right? Now come to the example 2. This is also very much similar. See here what is given in this example. This is the property 2. See, this is function 1, 4x cube. This is function 2, 3 upon x. This is the function 3, 5 e raised to the power 5x. This is the function 4. So this is an mixture of 4 functions and we have to integrate it. It means we will integrate each function separately. This is what the property refers in the earlier slide we have discussed, right? So 4x cube minus 3 upon x plus 5 e raised to the power 5x minus 2. This can be written as 4x cube dx, the first function, minus 3 can be taken outside, 1 upon x dx, plus 5 can be taken outside, 5 e raised to the power 5x dx, minus 2 can be taken outside, this is dx only. Now you know the integral of all. What is the integral of x cube? Integral of x cube is by using the formula of x raised to the power n, that is 4x power 3 plus 1 upon 3 plus 1. This integral of 1 upon x, we know that log x, so you will get here minus 3 log x. integral of e raised to the power 5x. Now see, if e raised to the power 5x is there, its derivative is what? 5 e raised to the power 5x, right? So I told you this is 5 is a number. In case of integration, this 5 will transform from numerator to denominator, right? So integral of e raised to the power 5x dx will be equals to what? E raised to the power 5x as it is, and this 5 will transform from numerator to denominator, right? And what is left here? This is 2 and dx. This can be written as 2 1 into dx. Derivative of x is 1, therefore integral of 1 is x. So it becomes minus 2x plus a constant is there, right? Likewise, you can proceed for this question. I would like to leave this you for an exercise. Try to solve the questions yourself, only then you will understand it, right? Otherwise, if I will solve every question, you can't understand. See this case, evaluate the following examples. E raised to the power x log a plus e raised to the power a log x plus e raised to the power a log a into dx. So before proceeding the solution of this question, let me recall some properties of the logarithmic functions. There are many properties of the logarithmic functions. I will not mention all those, but at least two properties are very essential here. Property 1 is what? Log x raised to the power p, this is always equals to p log x. Property 1. We will use this. And second property is what? E raised to the power log of x, its value is equals to x. This property is not true only for x. Rather, this property is true for any variable other than x. See, if I write like this, e raised to the power log 1 plus x square. See what happens here? X 1 plus x square is being replaced by x. So its value will become 1 plus x square. Are you getting the point? What I want to say, if x is being replaced by any other function, its value will be same. In general, if I write e raised to the power log of any function fx here, it is equals to always fx. So we will use this property and this property first, then we can solve this question. Look, let us take this question. E raised to the power x log a plus e raised to the power a log x plus e raised to the power a log a. So what they did first write it integral of the first function plus integral of the second function plus integral of the third function, because this is the sum of first, second and third function. So first we will write them separately. Now e raised to the power x log a, this is equals to what? Use this property. This x will transfer e raised to the power log a raised to the power x. This x will be transferred here by this property, right? E raised to the power log a raised to the power x, this is equals to this. Now use property this. By this, e raised to the power log x is equals to x. Here in place of log x, what we are having? We are having a power x. So its value will be what? A raised to the power x, right? This comes out to be a raised to the power x. The second term will come out to be x raised to the power a. Using these two properties, then the third will come out to be a raised to the power a. And you know the integral of all. Integral of a raised to the power x is a raised to the power x divided by log a. Integral of x raised to the power a is x raised to the power a plus 1 divided by a plus 1, and a raised to the power a is simply a constant, and integral of dx is 1 into dx, and integral of 1 is x. So we will get here a raised to the power ax, and the c is as usual constant of integration, right? Let us take this example also. You have to find out the integral of this function. See, dx divided by root x minus 5 minus root x minus 2. We did few questions of this type in case of derivatives. What we did? We rationalized such kind of function. So how we can rationalize it? In case of limits, we have seen many questions like this. Multiplying numerator and denominator by this. See, our denominator contains root x plus 5 minus root x minus 2, right? This is our denominator. So we will divide and multiply its negative sign, that is plus of this. So multiply this and divide this by root x plus 5 plus root x plus 2. So we are getting this step, right? We are getting here. So see, in denominator, this is a, this is b, a plus b, a minus b. So using the formula of a plus b and a minus b, this is equals to a square minus b square. So what we will get here? We will get here x plus 5 minus x minus 2, because if we will make a square of any square root, the square root is being removed, right? And nr will contain as it is. So simplify it. What you will get here? X plus 2 minus x plus 2, x and x will cancel out. 2 plus 5 is 7. So 1 upon 7 has been taken outside. What is left? X plus 5 raised to power 1 upon 2, because root x plus 5 can be written as x plus 5 raised to power 1 upon 2, right? Likewise, x plus 5 1 upon 2, x minus 2 raised to power 1 upon 2. Now you can use the formula of x raised to power n to find out its integral. And the integral of x plus 5 raised to power x plus 5 raised to power 1 upon 2 is what? X plus 5 raised to power 3 by 2 upon 2 by 3. So you will get here 2 by 3 x plus 5 x raised to power 3 by 2 plus 2 by 3 x minus 2 raised to power 3 by 2. 2 by 3 can be taken outside, so you will get finally this as a integral of the given function. So students, I think I should stop it here and we will consider the subsequent text in the next lecture, right?